Okay, so we're working through this section on statistical techniques, and if you remember what we did last week, we were looking at multivariate normal distributions, and we showed, we finished off by saying that in the general case, if you've got a vector of random variables, x here, that's multivariate normal with some general vector of means, mu, and the general variance covariance matrix, omega, and they could be dependent. These covariance terms can be non-zero. In that most general world, you can write down the joint density equation in this form here. And we derived it for earlier, sort of easier examples. We haven't derived it in this case, but it takes the same form as the ones that had come before. 2 pi to the minus n over 2. The determinant of this variance covariance matrix to the power of minus a half times the exponent of this quadratic form, where we've got a deviation of x from its mean as the vector, and the inverse of the variance covariance matrix in the middle, and a minus a half at the front. And that's the form of the joint density equation. Now, what we're going to start looking at today is a useful result to do with multivariate normal distributions, where we take a linear function of a vector of random variables that follows a normal distribution. And we can immediately say that if you've got a vector that's multivariate normal, so you've got x that follows a normal distribution, and x is a vector here, so this means multivariate normal, then if we take a linear function of the vector, that will also be multivariate normal. You know from stuff you did last year, if you take linear combinations of things that are normally distributed, the outcome is also normally distributed. Okay? Adding up weighted averages of normals still gives you normals. And the same applies here. It's just in a vector context that we're looking at it, but it's the same principle. So if we think of what a linear combination would look like in matrix form, well, we could multiply the vector x by a matrix of coefficients or weights A, and we could add on some constants, and this would be a general representation of a linear combination, a linear function of the x's, and that will then be itself multivariate normal. Now we can go a little bit further and say exactly what this multivariate normal distribution will look like in terms of the mean and the variance as related to the original mean and variance for the x vector here. So let's suppose that x is normal with some mean, and we'll just call it ex, we don't need any other notation, and a variance covariance matrix Vx. So that's the properties of the original x vector. What will the properties of the linear combination look like? Well, we can work out the results from the mean and the variance separately and substitute it in. We know that if we take the expectation of ax plus b, anything that's constant can come outside of the expectation. So the b can come outside, and the A matrix, that can come outside. The only bit that's a random variable in here is the x term. A and B are full of constants. So A is a matrix of constants. B is a vector of constants. So there's no randomness in those bits. It's only the x that carries a stochastic property. So we can immediately take the expectation through and write this as A times the expected value of x plus B. So our linear combination, ax plus b, we've said it must be multivariate normal, and now we know what the mean must look like. It must be A times the expected value of x, the original expectation, plus the b vector. And next, have a think about the variance. Well, remember what the variance is in these terms. It's a variance-covariance matrix. The variance of a vector is the expected value of the outer product of x deviated from its mean. So apply that to our linear combination here. We've got the expected value of the outer product of two terms, each of which is the thing we're dealing with, ax plus b, deviated from its mean. So we've got ax plus b minus its mean times the same thing transposed. That's the outer product, and then we take the expectation of the whole thing to get the answer, which is going to be the variance covariance for ax plus b. And this will be a big matrix. Variance is on the diagonal, covariance is everywhere else. But we can do a bit of simplification. We know already from the first bit that the expected value of ax plus b is a expected value of x plus b. So in here and in here we can replace expected value of ax plus b with aex plus b. We've got a minus outside of all of that, and the same thing in the second term as well. It's a carbon copy. And you can then see that the b's are going to cancel off. You've got a b here minus the b in the bracket there, same over here. So the b's will vanish and we'll just be left with ax minus a times the expected value of x in both brackets. Now in the next line what we're going to do is just bring a out. A appears as a pre-multiplying factor, so we can write that ax minus aex is equal to a into x deviated from its mean. Just bring a out the front. Remember, it has to be out the front because the order of multiplication matters with matrices. So we can't put it at the back, but we can pull it out the front or preserve that order of multiplication. And so in the first part, that's what we've done here, that an A has come out, and it can come outside the expectation because it's just matrix of constants, so we can pull the A right out outside the expectation at the beginning. Now for the second part, we've got ax minus a times the mean, which we can factor into a into x minus its mean. Now this time it's all transposed, so if you imagine the transpose of this now, it's going to be the transpose of that. And as we take the transpose through, we have to reverse the order, so this will be x minus its mean transposed a transpose. So in the second part, when we take the transpose through, the A transpose is going to come to the back, and we can also, because it's matrix of constants, it can come outside the expectation as well. So the A transpose sits right out at the right-hand edge, and the x minus its mean transposed, that all stays inside the expectation with the curly brackets. But then what you're left with in the middle, all of this stuff here, that is just the definition of the variance of x. If you skip back to what we had up a moment ago, that's your defining equation for variance covariance. The expected value, the outer product of x deviated from its mean. So we can replace that big box with simply the variance covariance of x. So that tells us then that our linear combination has a variance that is A times the original variance of X times A transpose. And that fully defines the multivariate normal then, because we've specified the mean and the variance covariance. If you write it in the notation that we've been using, if we say that X is multivariate normal with mean vector mu and variance covariance matrix omega, then AX plus B will be multivariate normal with mean A mu plus B, just substituting in for EX equal mu, and variance covariance A omega A transpose, substituting in for the variance of X being omega. Okay? So the rule at the bottom is the one to remember and that we'll use again. Taking linear combinations of normals. What you can see intuitively, we're taking a linear combination of x's here, and that maps straight through into the mean function. We take the mean of x and replace it with mu, but the form of the linear combination stays the same in the mean. When it comes to the variance covariance, the original matrix, omega, gets hit twice. It gets hit by A at the front and A transpose out the back. But the B doesn't make any difference. Remember, when you're measuring variances, adding means doesn't make any difference because it just gets subtracted off in the variances defined as a deviation from mean. So it all cancels off in the formula. So that's why the B goes. You can see that in this line. But we just need to worry about the multiplication side of it, and we get pre-multiplication by A, post-multiplication by A transpose. All right, has anybody got any questions about that? Okay. Another result we're going to look at, which is something we're going to use in the econometric work, involves a quadratic form equation where we've got a multivariate standard normal vector and a special type of matrix in the middle. So it's quite a specific result, but it does come up, and so we're going to derive this one. So it's a special case of X transpose AX. Remember, these are our quadratic form type of equations. But the one we're going to consider is where the X vector is a vector of standard normally distributed random variables. So that means that each individual X is normal 0, 1, and the different X's are independent of each other. Remember, we looked at that sort of case in the last lecture. That was our first building block when we looked at distributions of multivariate normals. So all different x's are independent. And we can write that as the vector x being multivariate normal with a vector of zeros for the mean, and the variance covariance matrix being an identity, because all the variances of the x's are equal to 1, and all the covariances are equal to 0 due to independence. So that's what's going into X in this quadratic form, multivariate standard normal. And the A matrix that we're going to have in our special case is a symmetric idempotent matrix. So remember, idempotent means that if you multiply the matrix by itself, you get back to where you started. And symmetric means the transpose makes no changes as well. So AA is A transpose is A transpose A, or AA transpose, they're all the same thing. Now what we're going to show is that in this particular case, the quadratic form X transpose AX follows a chi-square distribution with R degrees of freedom where this R, the number of degrees of freedom, is equal to the rank or the trace of the A matrix, the matrix in the middle of the quadratic form. And this is a useful result. This will become one of our sort of building blocks when we derive t-tests and f-tests, when we get onto the regression analysis. So that's why it's useful. Let's see where it comes from. The way we're going to go about proving the result, we're going to start by decomposing the matrix A into its eigenvalues and eigenvectors using that form that we saw in the matrix algebra section, where we write A as C lambda C transpose. C is the eigenvector matrix. Each column is a different eigenvector, and lambda is the diagonal eigenvalue matrix. Remember, we've got lambda 1, lambda 2 down to lambda n on the diagonal, zeros everywhere else. And we can always decompose symmetric matrix A into this form. Right, so let's start with that then. So we've just replaced A with C lambda C transpose. And just to make the arguments a little bit easier, we'll just change the notation briefly. We'll let C transpose X be denoted by Y. So you've got a Y at the back there, C transpose X, and at the front you've got X transpose C, which is just the transpose of C transpose X, so we can call that Y transpose. So we're now talking about Y transpose lambda Y. So let's just denote this Y vector as Y1, Y2 down to Yn. If we think about what is in Y transpose lambda Y, it would be, well, Y transpose Y1, Y2 up to Yn times the eigenvalue matrix that we just wrote up, times the Y vector again. Not transposed. Right, that's what that quadratic form looks like. Now if you multiply that out, what you get is the sum of each lambda I term multiplied by the square of the corresponding element from Y. So it would be lambda 1 Y1 squared plus lambda 2 Y2 squared, and so on. If you want to check that afterwards, just multiply that by that. You'll get a column vector with lambda 1 Y1, lambda 2 Y2 going down. Then do that row vector times the column vector and you'll get this. Sum of squared times the eigenvalues. Alright, so that just writes it in a different form, writes it as a sum of terms. Now, we can also think about the distribution properties of Y. Y is equal to C transpose times X. That's just copied down. And we know that X is multivariate standard normal. So it's normal nor I. So what we're taking here is a linear function of X. It's a matrix times X. So we can use the result that we looked at the beginning of the lecture. So if X is normal with mean mu and variance covariance omega, we had a result for the distribution of a linear function of X. Well, what we're doing here is we're pretty multiplying X by a matrix. We're not adding anything to it though. So it's a bit like this result, but without the B part, because we're not adding any constants on. But you can see the effect. The mean gets pre-multiplied by this matrix, The variance covariance, as we said before, gets hit twice, pre-multiplied by the matrix, post-multiplied by the transpose. So here we're going to have the same sort of idea. We start with normal naught I, pre-multiplied by C transpose. So the mean, which was 0, gets hit by C transpose at the front, but that's still going to be 0. The variance covariance, we start with I, we pre-multiply by whatever we're multiplying x by, C transpose in this case, and post-multiply by the transpose of it. Well, the transpose of C transpose gets us back to C. So we've got a C at the end there. The identity can be suppressed because it's multiplying other things. And you can see then that the variance covariance is C transpose C. And if you go back to our work on eigenvectors, the eigenvector matrix C is orthogonal. So C transpose C in all of this is equal to the identity, because eigenvectors are orthogonal to each other, and the inner product of a single eigenvector is 1, so you get that orthogonality result. So the C transpose C just collapses down to an identity, and we find that Y is itself multivariate standard normal. It's got the same properties as X. The fact that we've pre-multiplied by C transpose hasn't changed the properties. So in our vector Y, each element must be normal naught 1, and two different elements must be independent of each other because of that property that they're multivariate standard normal. Then we need one other piece of the puzzle, and then we can start to put the result together. And the other piece is that because A is symmetric idempotent, the eigenvalues can only be 0 or 1. We proved that as an exercise in the last lecture or the one before. There's exercises at the end of chapter 1. For symmetric idempotent matrices, the eigenvalues can only be 0 or 1. So, putting it all together then, our quadratic form, x transpose ax, can be written as the sum of eigenvalues times y squared from this part here. Now these eigenvalues can only be 0 or 1. So this thing is, well, in full it'd be lambda 1 y1 squared plus lambda 2 y2 squared, trivially all the way up to n. But these lambda coefficients in this weighted sum are only either 0 or 1. So if they're 0, say lambda 2 was 0, that's going to wipe that term out. It won't appear in the sum. If it's 1, then you just get the square of y. So this is going to be the sum of squared y terms, and the number of them is just going to be the number of times lambda's 1 rather than lambda being 0. So say n was 10, so we've got 10 of these terms added together. If 4 of the lambdas are 1 and 6 of them are 0, 6 terms are going to drop out, and then 4 terms are just going to be 4 different y's squared and added together. In total then, what you've got, this quadratic form, is a sum of r squared independent standard normals, squared y's, where r is the number of non-zero eigenvalues, the number of terms that are kept in. Now, if we have a standard normal random variable and we square it, what's the distribution? Squared standard normal? chi-squared, how many degrees of freedom? Sorry? If you've got one standard normal random variable and you square it, you get a chi-squared with 1 degree of freedom, right? There's only one thing, one random variable. If you square, that's what chi-squared 1 is defined by. It's the square of a standard normal. Now, if you have two standard normal random variables that are independent of each other, you square each one and add them together, you get chi-squared 2. Okay? And so on. If you had 3 of them, square them, add them together, as long as they're all independent, you get a chi-squared 3. And that's exactly what's going on here. Yeah, you've got squared standard normals, and you're adding them together because these lambdas are 1 for the cases where they're in, 0 for the cases where they're out. And so you're going to end up with a chi-squared distribution, and the degrees of freedom is just going to be how many of these squared standard normals you had in there. They're all independent normal random variables that are being squared and added. So in total then, x transpose AX is going to be chi-squared with degrees of freedom equal to the number of non-zero eigenvalues, because the number of non-zero eigenvalues dictates how many of these squared standard normals are being put into that equation. Is that clear? Okay. The last little bit then is just to remember that for a symmetric idempotent matrix, the number of non-zero eigenvalues is equal to the rank and the trace of the matrix, which concludes the result. So we can say that if X is multivariate standard normal and A is symmetric idempotent, then the quadratic form is chi-squared with degrees of freedom equal to the rank or the trace. It must be the same thing, it must be equal to the number of non-zero eigenvalues. And as we said, we'll use this in our regression work. Okay, any bits of that you want me to clarify? Are you happy? Right, let's move on then. So maximum likelihood estimation is our next section. This is going to bring us towards the end of our set of notes in section 2. And I think those of you who did introductory econometrics might have touched on this last year, but we'll go back over it and just sort of give you another introduction to what this is all about. Now, just as regression works for estimating coefficients in a linear equation that you will have done last year, maximum likelihood is also another sort of general and widely applicable technique of estimating population parameters. It can be used in a regression setting, but it can also be used in other settings as well. We'll consider it in a regression world when we come on to do the multivariate regression model later. But you will, if you carry on doing econometrics, you'll see it in other environments as well. You'll see it next semester in the time series work that you do there. Now, the idea of maximum likelihood estimation is that different populations give rise to different samples. A normal distribution with certain parameters gives a different lot of sample observations to a normal distribution with different population parameters. And what it's trying to do using maximum likelihood is say, well, given the data that we've got, which is the most likely population distribution to have generated the data that we've got. Let me do a little sketch and shove a page of blank in. Okay, let's draw 3 graphs. Actually, draw one big graph. I'll put it all on one graph. And let's suppose that we've got 6 observations on a random variable, and these are our observations. x1, x2, x3, x4, x5, x6. Alright, so that's our observations. We've gotten a sample from some random variable, and they're the observations that we've got. And let's suppose that we think these have come from a normal distribution with some variance. Let's just call it sigma squared, and let's not worry about that. Suppose we magically know the variance, but we don't know the mean, and we're trying to estimate the mean of this population distribution. So we're thinking, right, our data comes from some normal distribution with variance of 2 or something like that, and what mean might have given rise to these observations? Now, on one level, any normal distribution could have given those values. Yep, normal distributions give have support over the full range. So if I draw 3 different normal distributions, A, B, we need another colour now. Let's go for green. C. Right, now this data could have come from any of those distributions. These are normal distributions with a given variance, but they all have different means, obviously, because they're in different positions. But the data could have come from A, B, or C, because any normal distribution, it goes off to minus infinity down this way, it goes to plus infinity this way, and any finite set of observations are going to be covered by the support of that distribution. So it could have come from A, could have come from B, and could have come from C. But the probability of them coming from A is pretty small. All these observations are right out in the upper tail of the A distribution. So if you took 6 random observations from A, it's a bit unlikely that you'd get this collection here, because x5 and 6 are quite unlikely. You've quite a small chance of getting those, and the fact that we haven't got any in the main bit of the distribution and none from this side of the distribution, that would seem unlikely that it's come from A. It's even more unlikely to have come from C. All these observations are right down in the lower tail of C. The probability of randomly selecting observations from C's distribution and getting these outcomes is absolutely tiny. The chance of getting one of them would be tiny, let alone all 6. So it's really unlikely to have come from C. But then if you look at B, B is, the main mass of the distribution is right over the area where we've got our observations, x1 to x6. So out of the 3, you'd say B is by far the most likely distribution to have generated the data that we've got. So if you were having to pick a mean, you'd pick the mean of B, because it's way more likely than the mean of A or the mean of C to have given the data. A maximum likelihood estimation essentially takes that approach. It says, well, what data have we got? And given the data, what possible distribution could that have come from? And let's pick the most likely distribution to have generated the data that we've got. So if we were just focusing on this simple example, it would consider all possible normal distributions, consider a whole continuum of means, and pick the distribution for which this is the most likely, the most probable outcome compared to other normal distributions. So the way we formalise it, let the vector x, this is a vector, be a random sample of independent observations, so random drawings from some population So we'll end up with n observations, x1 up to xn. They'll be the elements of the x vector. And there's going to be some true distribution that has generated these data, and we don't know exactly what it is, but we'll just write it down as the joint density function f, which will be dependent on the output of the will be the one argument of the joint density function will be the vector x, the observations. The other argument would be the population parameters. So if this was to do with a normal distribution, theta would represent the mean and the variance, because that would be the thing that governs the normal distribution. But in very general terms, we'll just write theta down as a k/1 vector of population parameters. And that's going to be the thing we want to estimate. And what maximum likelihood does then is it picks theta so that the corresponding joint density function is the most likely one to have generated the observations or the sample that we've got in our x vector. Okay, so you have to assume a form for the joint density. So we're going to assume the data's come from a normal or from a t distribution or something like that, and then say I'm going to estimate the parameters of that distribution so as to make the population one that's implied be the most likely one to have given me the data that I've observed. Now the way we actually do it in terms of the mechanics of doing maximum likelihood estimation, you start off with your joint density equation. We've written down some of the forms of these if we were dealing with normally distributed data, but you can write down the forms for other types of distribution as well. And we call that the likelihood function. Now the likelihood is just another term for the joint density, but we sort of change our understanding of what the equation means, but the formula doesn't change at all. So in terms of suppose we had normally distributed data, the joint density equation would take the form that we were looking at in the last lecture. We would now say, okay, this is our likelihood equation. So the equation is just a carbon copy of the joint density function. But we sort of change our understanding of what that equation represents in our minds. Normally with a joint density, you're saying, well, the joint density equation is given and the population values of the parameters are given. We've got a normal with a mean of 2 and a variance of 3, say. The population is fixed. And then we talk about the likelihood of getting different samples from that population. So we think of the equation as theta being given and x varying. The sampling varies, the outcomes, the drawings from the distribution vary as we take samples from that distribution. With maximum likelihood, we think of it the other way round. We think, well, I've got my data, that's x, and that's fixed, that's given, and now I'm going to think about all sorts of distributions that might have generated x. So I'm going to think of all, in a normal distribution example, you might think of all possible means and variances, all possible different thetas that might have given the sample x. So in a joint density environment, you're kind of picturing theta as being fixed, and x varies as you go sampling. In a likelihood situation, you've got your sample, so x doesn't change, and you're imagining different thetas. But it's the same equation. Right, so that's the definition of the likelihood. What we do next is maximise it, as the name suggests. You maximise the likelihood with respect to theta. And so at this point it just becomes a calculus problem. You've got your equation, L, and you want the maximum, so you differentiate with respect to theta. This usually involves partial differentiation with respect to a vector of different population parameters, theta. Set equal to 0, to give you your first order condition, and then solve it out. And we're going to use the notation for maximum likelihood estimators, theta with a tilde, to denote that we're using maximum likelihood estimation. Now, in practice, a lot of likelihood equations are awkward to do direct differentiation on. An alternative is to use the natural logarithm of the likelihood equation rather than the likelihood itself. So you could maximise the log of the likelihood with respect to theta in the usual way, differentiate, set equal to 0 and solve. And because taking logarithms is a monotonic transformation, you get the same answer for theta tilde, whether you differentiate the likelihood and solve that way, or differentiate the log likelihood and solve for theta that way. So very often we'll deal with the log of the likelihood because it linearises the equation and makes the differentiation easier, but it will give us the same answer. So it won't matter which way round you do it. Now the reason maximum likelihood's used is because it has some quite nice properties. Now proving these goes beyond the scope of our module, but just to sort of mention what they are, under sort of broad assumptions, the maximum likelihood estimates are consistent, which means as we get more and more sample data, the estimates get closer and closer to the true population values. So the mean of the estimates converges to the true values, the variance of the estimates converge to 0, so they get more precise the more data we have, and that's a nice property that we would want for estimators. Asymptotically, which means in large samples, as the sample size goes towards infinity, the maximum likelihood estimates behave as if they're normally distributed, even if the underlying distributions involved aren't normal. So in large samples we can treat maximum likelihood estimates as being normally distributed, and that allows us to build hypothesis testing procedures based on the maximum likelihood estimates. And also in large samples the maximum likelihood estimates are efficient, so they're as precise as they can be within a certain class of estimator in large samples. More specifically, we can say that no other consistent and asymptotically normally distributed estimators have a smaller variance. So that means that these estimates are really precise. The variation is as small as it can be within this class of estimator that is consistent and asymptotically normal, like maximum likelihood are. Okay. So I think we'll stop there, but we'll go on to an example of maximum likelihood estimation next, but we'll do all that in one go tomorrow. So see you tomorrow.